Hi together and welcome to the final part of our Lifehack series with focus on optimization. In the previous Lifehacks we showed you the different steps of an optimization workflow. Today we will have a look to several post-processing options. First, the scatter plots. Here you can see not only the development of the parameter values during a database or optimization run, it is also possible to check the results. For example, like it is shown here, the efficiency over the total pressure ratio. Of course, you can also zoom in on the area of interest. You can also change the presentation of the individual results here, so that, for example, invalid designs that violate a restriction or a constraint are marked here with small circles. Also, a Pareto front can be displayed with this type of plots. Further, you can get all the parameter values together with the results in a table. If a constraint is not fulfilled, the value is colored in blue for lower or in orange for upper bound violation. Parallel coordinate plots, or PCPs, are suitable to compare a lot of variables. So one can easily get an impression of the relationship between parameters and/or responses using such plots. Please notice that in these plots are all values normalized. In this plot of a PCP you can see the influence of the relationship of the constraint for torque to the values of the parameters and the objective. And we can see on the first view that this constraint does not prevent us to get the highest of efficiency. Also, one can see which designs would be excluded if we limit parameter bounds. For this, a slider can be used and moved up or downwards, like it is done here for one parameter. Every sample which is excluded with this limitation is shown in light gray. Let's come to monitoring an optimization run. Here on an example of a single-objective optimization. The two curves showing the evolution of our objective, in this case the efficiency of the designs, whereby the dashed line marks the value predicted by the surrogate model and the other the simulation value. The evolution over the design iterations can also be shown for our constraints, here for the torque. Also, the quality of the surrogate model can be monitored over all designs iterations of an optimization. So we can see here that the surrogate model was improved from a correlation value of 0.84 to over 0.9. And we can check the development of the evolutionary algorithm for the current or last valid designs over the generations. All of these monitoring plots can be followed live during the optimization run. Finally, we can do some data mining. We have already seen the leave one out analysis in the previous Lifehack database. Here the prediction by our surrogate model for our target and for our constraint is pretty good, with a value above 0.9. Let's move on to another analysis method, the so-called self-organizing maps, or SOMs. The idea behind is to project high-dimensional data onto a low dimension in this case a two-dimensional map. This map is created by an artificial neural network that is trained using unsupervised learning. It is a tool for reducing the dimensionality of the data and for visualization. This is useful for discovering important trends and discovering correlations and anti-correlations between parameters and/or responses. It becomes much clearer when we look at the maps of our target and limitation. Here we see the map for our target on the left and our constraint on the right, marked by the red line at 850 Newton meter. We have told the optimization tool that this is a forbidden zone and no design in this area is allowed. Luckily, we can see that the area of highest efficiencies is in the lower right corner, where we do not have too high values for the torque. This is not the case in all optimizations. Sometimes different targets and constraints exclude a good or a better design. Last but not least, a quite important analysis method is the analysis of variances, or ANOVA. This is a sensitivity analysis to determine the effect of varying input or model parameters on the variation of the output. Usually, these are our target or other simulation results. This allows us to see which parameters have the greatest influence on our result values. Important to say is that behind the sensitivity analysis, a Monte Carlo integration is done with a certain number of samples and iterations. The right number for samples and integration is problem dependent, so to get a good result, more than one run should be performed with different number of samples. In addition, the impact of the local variance can be shown in a diagram. Here, the impact of the parameter S2 camber beta 1, which has the most influence on the efficiency. That's all for the moment. I hope you enjoyed this life hack. In case if you have any questions or comments, please leave us a message below this video. If you are interested in our software solution for optimization, please don't hesitate to contact us. Thank you for your attention and see you next time.